Detecting heart disease through early stage signs is a major concern. This will lead to death if not diagnosed in time. The precise decision support system will play a key role in early stage diagnosis of heart disease, where heart specialists in isolated, semi urban, and rural areas are not available. Machine learning has been successful in helping to decide and forecast the vast volumes of data generated by the health sector. This is our MEEN 423 project on development of a machine learning derived support system for ischemic heart disease diagnosis. The primary objective of this project is to develop a supervised machine learning algorithm that can accurately determine and stratify chemical heart disease patients who are at risk for future major adverse cardiovascular events, MACE, including ACS, stroke, or death. Every 36 seconds, an individual dies of a heart disease. The data used for the purpose of this experiment was the heart disease data from the UCI repository. We have 14 features.
Before using the data for training any algorithms, it should be first processed for outliers. Outliers are points outside of statistical ranges and are due to two main reasons, either error in recording the data or medical significance. The data we have showed 4 instances where the outliers were outside of the main ranges, but these instances were kept since they are suspected to have medical significance. The second step in data processing is normalizing the data. This is because the features in our data have different scales, and thus they need to be unified between 0 and 1 using the following equation. These are the numeric variables in our dataset, and this is what they look like after normalizing.
Using MATLAB's integrated machine learning tool, we began modeling the system. It was discovered that KNN provided the best results with an accuracy of 60.4, but we realized this value was too low compared to literature, so something had to be done. We tested modeling the data with fewer response values. Instead of the data ranging from 0 to 4, we ranged it from 0 to 1, making it binary classification. It was after this adjustment that the model started providing better results, reaching an accuracy of 83.8. Hyperparameter tuning led to a model accuracy value of 84.8%, with 45 nearest neighbors. This number exceeds that of literature expectancy, which is around 18. This raised concern of overfitting our model.
Class imbalance in our data suggests that the unequal number of healthy and sick patients used to train the algorithm causes bias. To eliminate this imbalance, we have two major techniques. We can either undersample the majority, which is the healthy subjects, or oversample the minority, which are the sick subjects. After training the model with both the undersampled majority and the oversampled minority, we noticed that oversampling provided the best accuracy at 90.3%. It also provided the best combination between specificity, sensitivity, and precision out of all the three data types.
It was found that the final model produced exceeded accuracies expected in literature, which is a great milestone achievement. Our model can predict heart disease in patients with over an accuracy of 86%.
We'd like to conclude that this was an invaluable experience learning more about artificial intelligence, which is the future of data analysis. We'd like to thank you for your time, and hopefully this was an eye-opening experience in how machine learning, a few lines of code, and techniques could possibly save a life from the risks of heart disease.